this, and he will tell us how a VM can help a profiler to be accurate despite the presence of dynamic compilation and optimization. So, please.
Thank you. So I'm Yudi Zheng from the University of Lugano in Switzerland, and today I would like to talk about accurate profiling in the presence of dynamic compilation. Before studying the problem, I would like to introduce some general concepts. The first one is dynamic compilation. So nowadays, the managed runtime system, such as Java Virtual Machine, are often consist of two components, the interpreter and the dynamic compiler. The code representation that run on top of it, in the case of Java Virtual Machine, the Java bytecode is first interpreted by the interpreter, and then later the frequently executed part of them will be compiled by the dynamic compiler. So to perform dynamic analysis on top of the bytecode, we often employ the bytecode instrumentation, which is for specific target behavior, we actually insert a bytecode sequence to, let's say, emit an event representing the occurrence of such target behavior. So the issue is actually here, from the point of view of Java Virtual Machine, it cannot tell the inserted code from the base program code. So this actually leads to a perturbation problem of the bytecode instrumentation. So now that we know that the inserted code intercepts the target bytecode, what if? First of all, if the target bytecode is actually optimized and eliminated. So in this case, you will have your inserted code still there, but emitting an event which does not happen. Or second, the target bytecode is actually should have been eliminated, but your instrumentation actually perturbs the optimization, which prevents the target bytecode being eliminated. So in this case, although your instrumentation actually emits an event that does happen, but it doesn't, the program behavior is actually changed from the version without instrumentation. So to illustrate these issues, actually I come up with this example that you could see on the slides. So on the left-hand side, you do see a Java code snippet, which is a new statement and invocation guarded by a if statement. And the invocation uses the allocated object as the receiver. On the right-hand side, you do have an intermediate representation graph, which is the and here you actually have the rectangle node as the control flow node. You have the rounded node as the floating value node. You have the bold arrow as the control flow edge, and the other edge as the data flow edge. So here I actually simplify the IR. You don't see the invocation to constructor here, just to clarify. So there are actually some kind of escape analysis that could work in this situation. So there is a context-aware escape analysis called partial escape analysis presented by Lucas Starter in CGO 14 and others in CGO 14. So the basic idea is here, when we see this allocation, we can actually try to figure out if it is escapes in each branch. So let's assume there's no further usage of the allocated object A, and the invocation to foo is not inlined. So in such case, we could move the allocation into the if-then branch. So in this case, if the branch is not taken, actually the allocation will not be there because it's not needed anyway. So in this case, it actually saves some memory. Okay. So coming back to our issues, the first one is like, okay, we insert something there to intercept an allocation. So because of the partial escape analysis, the allocation is actually moved into the if-then branch. And in this case, you can see our instrumentation is actually emits an event that is not existing. So let's assume we have 1,000 execution of the code snippets during for the compiled code during the compiled mode. So indeed, we have actual allocation of 100. We intercept allocation of 1,000. Without instrumentation, is 100. So in this case, definitely is overprofiled. The same case went into if we want to, if we wrap the allocated object as the event content and send it to our profiler. So in this case, we actually create an additional data dependency, which prevents the partial escape analysis to be effective. So in this case, again, we can see how many there. For 1,000 execution, we actually allocate 1,000 objects. We intercept 1,000 objects. But without instrumentation, there is only 100. Again, it is still overprofiled because it does not map to the actual program behavior. So we come up with this approach. The basic idea of this approach is like we isolate the inserted code from the base program, program. And we also provide certain APIs to allow the Bytecode instrumentation to query about the compiled decisions, which I will show later. So there are certain assumptions that we made. First of all, our approach works on the method-based compilation. We currently do not explore into the trace-based compilation yet. The second one is our approach works on the IR-based compilation. It has to be single static assignment form. We require the dedicated IR node representing the entrance and the exits of the method. We also require dedicated IR node for merging the control flows. These are for simplifying the algorithms. I mean, it could be complicated and remove this kind of assumptions. Yep. So the final one is like we actually target only single-tier compilation. To enable our approach on multi-tier compilation, you have to increment our approach on each of the dynamic compilers. So it's still doable. The actual approach is like we, first of all, we extract the inserted code from the base code IR graph. And these are actually categorized into an inserted code subgraph. We call it ICG. The second step is like we actually associate these ICGs with the base program IR node. There still could be some data flow originating from the base code IR graph to our ICGs. In this case, these kind of data flow edges are weakened, and they will not prevent the any other dynamic optimization to be effective. So to enable the distinguish between the inserted code and the original base program, we actually force the Bytecode instrumentation to invoke our delimitation API to mark the boundary of the instrumentation. So during the dynamic compilation, we actually perform reconciling operations on the ICGs whenever there is a no operation on the base program IR node. And towards the end of the dynamic compilation, we splice the ICG back into the original IR node before generating the binary code. So the delimitation API basically consists of two methods, the instrumentation begin and instrumentation end, marking the beginning and the end of the instrumentation. The instrumentation begin also takes a parameter, which can be the value of pred, suc, or here. Pred, suc basically associate your ICG with either preceding or the succeeding IR node. Or here, you basically anchor your ICG to the instrumentation's original location. So talking about reconciling operations, we actually categorize node operations into different classes. For example, we do have this node elimination. We have the value replacement. Node elimination is basically for, let's say, it could be using the deco elimination to remove the certain IR nodes. So in this case, we remove the associated ICG as well, if there is ICG associated to this node being eliminated. Value replacement is basically replace a value represented by a node with another value represented by another node. In this case, we also update the weak data flow edges of the ICGs that if there is some dependency from to that node. Also, if there is a node cloning, which is very common if you unload a loop or doing some kind of loop optimization, basically. You also clone the associated ICGs such that we have a clonal ICG that will be inline later separately. In terms of the node expansion, which is very common in case of lowering, which lowers a high-level IR node to a low-level IR node. So in this case, we also update the associated IR node because the previous one is kind of expanded. So in the very last case, if there is no movement, we don't do anything. Because actually our ICG still follows still associated with the with the original node, and in case of movement, we don't need to change it. So in this case, we can actually compose those sub-operations into optimization. For example, the partial escape analysis we talked about, it consists of a set of node cloning and value replacement operations, and then the final node elimination of the original allocation node. Of course, we can also compose the other optimization like inlining or lowering. So back to our example. Okay, first of all, to enable our approach, you simply have to wrap the instrumentation with our delimitation API like this. So in this case, our dynamic compiler can tell the exotic code and then extract it out. Basically, we have on the right-hand side, you have an ICG associated with the allocation node. So the first step of the partial escape analysis actually it forks the allocation node to the branches. Currently there is only one. It could be many. So into the branches. In this case, we also fork the ICGs. So the second step is like value node replacement, replacing the original allocation node with the cloned node. And in this case, we also perform an update of the weak data dependency in the lower ICG. So the final operation of the partial escape analysis is actually it removes the original allocation node. In this case, we also remove the associated ICG with the original allocation node. So at the end of dynamic compilation, you actually splice the ICG back into the original IR graph, and as you can see, our instrumentation actually follows the allocation and to emit the allocation events to where it does exist. So as I said, we also provide a certain set of query intrinsics. For example, we have its method compile returning true in the compile mode, but false in the interpreted mode. We have its method inline that returns true if the enclosing method is inline. This could be very handy if you want to guard some profiling in the getter and setter, using the negate of it. If you don't want the profiling of getter and setters if they are inline. Also, we have get root name return you the compilation root name. We have get log type, which return you integer representing the runtime path that is taken for this dedicated allocation operation. For example, you have allocation that could be going into the thread local allocation buffer or directly on the heap. In this case, we can return you an integer representing each path. And also, you have the get log type. In Java, in JVM, you have monitor enter, which could be bias or compare swap or other heavy locking operations. In this case, the get log type actually returns you the actual path that is taken. You can know that the preceding monitor enter is kind of like bias locking or compare swap or others. The programming model of our approach is relatively simple. So when you have an already existing approach, you basically choose an associated bytecode and wrap the instrumentation with the invocation to our delimitation API. So for supporting this, we actually modify DISO, which is a domain-specific language for instrumentation, to automatically insert such invocations. So you don't have to worry about it. But later, I will still show you how you could construct it without using DISO or actually without using this option enabled. So the second step is like you have to refine your instrumentation. You have to keep in mind that this is not the normal instrumentation anymore. You have to keep in mind that the exotic code will follow the bytecode. So in this case, your exotic code will also follow the allocation to where it is actually happened. And also, the incoming data flows might become unavailable. This means that if you want to profile the receiver of an invocation, and then you have your invocation in line and your receiver being unavailable. In this case, we will replace the data dependency to the receiver to be a null value instead of this. So in the last step, you can actually use the query intrinsic to limit your profiling scope. For example, you can use its method inline, its method compile to limit your profiling only in the compile code. or you can provide more information in the immediate events. So here I show you an instrumentation example. This is diesel code. I don't want to go into details, but basically it says for each new bytecode, I insert after that the method body of this method. So basically a profiler.profile allocations. To enable our approach, you simply has to wrap the instrumentation with our delimitation API. So this actually tells you the actual allocation that is happening. To be able to calculate the stack allocation, you actually can also perform another instrumentation. There is the naive one. If you don't want your instrumentation to perturb the inlining, you can also wrap it with our delimitation API to make it using our approach. So as I said, we can also use the query intrinsic. For example, here I got our profiling with the static query is method compile, so it only profile in the compiled mode, and also we can pass the alloc type to our profiler. So in this case, actually, because it's compile time constant, it will be. I mean, this actually returns true in the in the compiler. So it will remove the if statement because of the dynamic compiler. So the actual implementation is based on Oracle's compiler, and our programming model has improved a lot thanks to the OOPSLA's reviews. And our implementation is now integrated into OpenJDK graph, and certain API actually changed because of due to the code reviews from the OpenJDK community. So some experiment results, we actually can use our approach to improve existing profiler. Because, for example, just now we have this allocation profiler, and we can use it to profile for each allocation sites the how much stack allocation that is happening there. Here we actually sum up all the data from all the allocation sites in Type benchmark sheet. So as you can see, actually contributes like 8% of the total allocation are stack allocated. There are some exceptional things happening in the first iteration because of the startup of because of the initialization of the benchmarks. So there is also a very outstanding one, Sunflow, which actually allocates 30% of the allocation on stack, and which accounting for almost 700 megabytes of data. So this would kind of affects the garbage collection behavior very much, we assume. So we actually took a look at the object lifetime. So in this case, we actually use a object allocation counter as the object lifetime metric, virtual object lifetime metric. If you're using naive instrumentation, then you basically come up with a histogram like this. So the bins on the left represents the shorter-lived objects, and the bin size are actually log scaled. So if you enable our approach, actually it becomes like this. So it dramatically decrease the value. But still, you notice that at the very left bin, there is an increase. This is because actually partial except analysis try to postpone the allocation to where it is needed. So that's why we have some of the objects shift to the very leftmost. So we can also do some other, we can improve some other profiling. Like in this case, we can profile the method calls. So as you can see, I don't want to go into details. The summary is just like 92% of the invocations are actually inline, so that you don't have to profile here. Of course, we can use our approach to enable new kinds of profile. For example, taking the callsite profiler, we can actually combine it with the inlining log printed by the dynamic compiler. So in this case, we can reason about what kind of reason for non-inline callsites and how many are they. And I mean, here I select the hottest, but polymorphism-related reasons for each callsite. You can also attach a receiver type profiling with the calling context. Okay. So I'm almost done. So of course, you can also use our approach within the source code to create some kind of assertion-based unit test. So to conclude, I first introduced the perturbation problem of the Bytecode instrumentation. I show you the approach of how we isolate the inject code and to reconcile it. I show you a list of query intrinsics that could be used by the bytecode instrumentation to provide more information or limit your profiling scope. And I show you some experimental results. So with this, I conclude my talk, and I'm happy to take your questions.